Hi guys, this is O-Level Chemistry, Paper 4, Specimen 2023, Question 1. Liquid Q is a fraction from petroleum containing large alkane molecules. Figure 1.1 shows the apparatus used to crack liquid Q. The vapor from liquid Q is passed over heated aluminum oxide to produce a mixture of hydrocarbons that includes alkenes. So now this setup is shown over here. Look at the setup in detail. Part A asks us identify the two pieces of apparatus by completing the boxes in figure 1.1. Now the box at the top is pointing at the stand that has the boiling tube connected to it, which it is holding, through which the delivery tube is passing into the water trough. And the second box at the bottom is the boiling tube that is collecting the gas that is being produced. So the first box that is on the top of the page, we will call it or rather label it a clamp stand. There is another name for it that you guys need to know as well. It is called a retort, R-E-T-O-R-T, retort stand. Either of the two names will be okay here. And the second box, we will label it as a boiling tube. Now, since they have not specified whether this is a boiling tube or not, a test tube, if labeled here, will also be acceptable. Part B asks us, state the purpose of the mineral wool. Now, the mineral wool is kept inside the first boiling tube that the stand is holding to soak up the liquid. So, that is exactly what we will write here, to soak up, or if you want to be more specific, to absorb liquid Q. That is what they have labeled it. Part C, give a test and the result that shows the presence of an alkene. Now, the test for an alkene is the addition of aqueous bromine. So, test we would write add aqueous bromine, which is Br2 aqueous. And the result that we will obtain would be that the color changes from brown to colorless, or we can write that the brown color of bromine is discharged because bromine adds onto the alkene. So color changes from brown to colorless. Part D. State why the delivery tube must be removed from the water when the heating stops. Okay, this is a very important precaution that needs to be taken when you're heating the apparatus, or rather, the apparatus is already heated, right? And when you stop heating the apparatus and you have the delivery tube present inside water, there is a difference in pressure that is created. And because of the difference in pressure, when the apparatus cools, the liquid is taken up into the apparatus, the glass apparatus. Now, this is dangerous because the glass apparatus is still hot and the water or the liquid is relatively cooler. So, this liquid might be able to crack the heated glass apparatus. So, this should not happen. So, how do we write this? We write so that suck back of water. This is what it is called. Suck back of water is prevented when the apparatus is cooled. Question 2. A student investigates the reaction between aqueous sodium carbonate and two different solutions of dilute hydrochloric acid labeled solution A and solution B. The equation for the reaction is given. Sodium carbonate reacts with 2 moles of HCl, producing 2 moles of NaCl, 1 mole of water, and 1 mole of CO2. The student follows the instructions for the three experiments. So now experiment 1. Use a volumetric pipette to add 25 cm cube of aqueous sodium carbonate to a conical flask. Add thermophthalene indicator. Fill a burette with solution A. Record the initial burette reading. Add solution A from the burette until the solution turns colorless. Record the final burette reading. Table 2.1 shows the student's results. Calculate the initial burette reading for the experiment 1 and record it in table 2.1. Okay, so this table says that the final burette reading is 13.2 and the volume used is 13.2. That means initially the reading must have been set at 0 so that the final reading is equal to the volume used. So we would add here 0.0 since all the readings given in the table are to 1 decimal place. Experiment 2. Empty the conical flask and rinse it with distilled water. Repeat the method in experiment 1 with methyl orange indicator instead of thermophthalene indicator. Part B. Figure 2.1 shows the initial and final burette readings for experiment 2. Okay, use figure 2.1 to complete table 2.2 for experiment 2. Okay, so initial reading is at, so if you look at this closely, 12.5, 12.6, 12.7, and 12.8. So this reading is at 12.8. Initial reading we will include in the table as 12.8. And the final reading is 39.1, 39.2. It is at 39.2. So the final reading we would write as 39.2. Now we would subtract 12.8 from 39.2 to obtain a value of 26.4 as the volume used. Part C. Methyl orange indicator is red orange in acidic solution and yellow in alkaline solution. State the color change observed in the conical flask in the experiment 2. Okay, so in the in our conical flask we have the base present, right? The alkali present. So the color in the conical flask would be yellow, and we added acid from the burette. So the color would change from yellow to red because methyl orange is red in acids. Part D. Suggest one observation other than color change that is made when dilute hydrochloric acid reacts with aqueous sodium carbonate in experiment 2. Okay, so basically here an acid is reacting with a carbonate, so definitely carbon dioxide would be produced during this reaction. And how is that observed? We write effervescence, 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 and a colorless gas evolves. Experiment 3. Empty the conical flask and rinse it with distilled water. Empty the burette. Repeat the method in experiment 1 with solution B instead of solution A. Use thermophthalene indicator. Table 2.3 shows students' result for experiment 3. Here, the volume used is 6.6. Okay, part E. Complete the sentence. Experiment dash used the largest volume of dilute hydrochloric acid to change the color of the indicator. So we need to recall experiment 1 used 13.2 cm cube of acid, whereas experiment 2 used 26.4 centimeter cube of acid, and experiment 3 has used 6.6 cm cube of acid. So it is asking which experiment used the largest volume. So the largest volume was used by experiment 2. Part F. State the effect on the volume of solution B used in experiment 3 if aqueous sodium carbonate is warmed before adding solution B. So a change in temperature will not have any effect on the volume. So effect on volume used, no effect. And what is the reason for this? The reason is that changing the temperature does not change the concentration. So we will write the concentration remained the same. As long as concentration remains the same, then we will also have the same volume of the same substance, right? So if we change the concentration, then the number of moles will change. So we will change the volume in accordance with the change in concentration. But increasing or decreasing the temperature will have no effect on the concentration, so no effect on the volume as well. Part G. Calculate the simplest whole number ratio of volume of solution A used in experiment 1 to volume of solution B used in experiment 3. In solution 1, the volume used was 13.2 and the volume used in experiment 3 was 6.6. If we divide 13.2 by 6.6, we get a value of 2, so the ratio becomes 2 is to 1. Part 2. Calculate the simplest whole number ratio of concentration of solution A, which is again 13.2, to concentration of solution B. So the volume of solution B was 26.4. So if we divide 26.4 by 12.2, we get a ratio of 1 is to 2. So the ratio of A to B is 1 is to 2, and the ratio of A to C in the previous part was 2 is to 1. This is the same as the ratio of the concentration. Okay, part H. The burette is emptied and reused in experiment 3. Suggest an additional step after emptying the burette which would improve the accuracy of the results. Okay, in order to improve the accuracy of the result, what we must do is we must clean the burette completely with any other solution present in it. So after we empty it, we actually add the solution, in this case solution B, right, into the burette, and then we wash out solution B from the burette. So now if there was anything that was present in the burette, that is now removed, and the only thing now present inside the burette is solution B. So when we fill it up with solution B, there would be nothing else that would interfere with our result or anything that would either dilute or react with solution B. So we would write the burette should be rinsed with solution B in order to remove traces of any other solution that was previously present in it. That was previously present in it. Part I. Titrations often give inaccurate results if done only once. Suggest how repeating each experiment several times produces more accurate values. Okay, so now when we repeat an experiment, we actually obtain similar results by repeating it multiple times. We sometimes also end up with results that are not similar. So those are called anomalous results and we omit them, right? So now when we repeat the titration and we get similar results, so what we do is we add up those results and take the mean value. When we take the mean value tends to be more accurate than any of the individual result that we obtain. So this makes our results more accurate. So repeating of the experiment and taking the mean value. This is the text that we should put down here. So we will write repeat several times to obtain similar results and take their mean. The mean value would give us a more accurate result. Okay, we should also mention here omit anomalous results. Experimental errors should be avoided over here. So in this way, if we take the mean of all the correctly performed experiment, the values of all the correctly performed experiments, that mean value will be the most accurate value that we have. Question 3. A student tests two solids, solid C and solid D. Test on solid C. Table 3.1 shows the test and the student's observation for solid C. Okay. Appearance, it's a green solid. Okay. Test 1, when you heat it, the solid turns black. Okay. Test 2, add dilute sulfuric acid. Rapid effervescence. Okay, if you're getting effervescence on addition of an acid, most likely this effervescence is CO2. Now test the gas produced. Lime water turns milky. It is confirmed that this is CO2, and because CO2 is released, that means our salt contains carbonate ions. So test 2 has shown us that carbonate ions are present in our solid C. Test 3. To the solution produced in test 2, add aqueous ammonia dropwise and then in excess. The result, a light blue precipitate forms, which dissolves to form a dark blue solution. This is the test for the presence of copper ions. So, test 3 tells us that copper ions are present in our solid C. Okay, part A. Test 1 states that solid is heated. Suggest why it is necessary to heat gently at first. Okay, there are two reasons. One reason is that the glassware that we use, test tube, right? If you heat it strongly in the beginning, there is a highly likely chance that it might crack. So we should stop that from happening, or rather prevent it from happening. And the other reason is when we heat a solid, it decomposes. When it decomposes, part of it is removed in the form of a gas. So in this case, CO2 is given off, right? So when CO2 is released from the solid lattice, the lattice breaks open. When it breaks open, parts of the solid might come out of the test tube. This is known as spitting of the solid. So we should stop the solid from spitting out because that will actually interfere with our result. If we are actually requiring to have the mass calculated or measured at the end, then loss of mass from the test tube would result in the experiment going all wrong because some of it would be lost, right? So the reason here would be so that the solid does not spit out of the tube, and the other reason was, and also because the tube might crack on strong heating. Part B. Describe how you would use lime water test to test the gas produced in test 2. Okay. So it's a 3 mark question. So we need to have this described in detail. So what we will do, place a rubber bung with a delivery tube on the tube in which acid is added. Place the other end of the delivery tube inside a test tube containing lime water. Bubbles of gas would be seen in the lime water. So when bubbles of gas will be seen in the lime water, and if this is CO2 gas, then the lime water would turn milky. Okay, part C. Identify the gas produced in test 2. This gas is carbon dioxide. We can also mention its formula, CO2. And the next part asks us, identify solid C. So solid C, we have concluded that it contains a carbonate ion and it contains copper ion. So in all likelihood, this is copper 2 carbonate. We can also include its formula as CuCO3. Next, test on solid D. Solid D is potassium iodide. The student makes an aqueous solution D using solid D and divides it into two portions. To the first portion of solution D, the student adds an excess of aqueous sodium hydroxide. Complete the expected observation. So when sodium hydroxide is added to potassium iodide, there is no visible observation with potassium or any visible observation with iodide ion. So no visible observations here, right? Part F, the student tests the second portion of solution D to show the presence of iodide ions. Give the test and the result that shows the presence of iodide ions. The test would be add nitric acid followed by aqueous silver nitrate, which is AgNO3. Now, when you add silver nitrate, iodide ions would react with the silver ions that you add to form silver iodide, and silver iodide is yellow in color and it's a solid. So, result is yellow precipitate of silver iodide, AgI, is formed. Part G. The student does a flame test on solid D, complete the expected observation. So, a flame test would test for the presence of the metal that is present. So, in this case, since it is potassium, the flame would turn lilac in color. So, the observation would be a lilac flame. Part H. Describe how to do a flame test. And this is for 3 marks. So this needs to be explained in detail. So what we will do is using a clean wire or a wire loop, whichever we recall. Take solid potassium iodide on it. Place this in a hot blue flame. When you turn on the Bunsen burner, you should make sure that the flame turns blue, right? That is the hottest part of the flame. So place this in a hot blue flame and observe the flame color produced. You can also record it. When you place potassium, you will end up with a lilac flame. Another thing that you can do, you can take a splint, a wooden splint, you can dip it in a concentrated solution of potassium iodide and then place this in the hot flame. This will also give a slight lilac flame when the potassium ions in potassium iodide are burnt. But heating the solid would definitely produce a more observable result as compared to when you place a splint in a concentrated solution, burn that. Question 4. Plant leaves contain a mixture of colored substances. Plan an experiment to find the RF value of colored substances present in plant leaves. Your plan should describe the use of common lab apparatus, plant leaves, sand, ethanol, as the solvent and absorbent paper. You may draw a diagram to help answer the question. Okay, the first thing is we should actually come to the conclusion that we are performing paper chromatography here. Then first we will draw the diagram. This is our paper which they call the absorbent paper. We will draw a baseline on it and we will place a sample of our plant leaf solution here. And now we label this. This is called the absorbent. Absorbent, absorbent paper. This is called our baseline, and this is our sample spot. Okay, so now we have prepared our paper for performing paper chromatography. In the next diagram, we will draw this same paper, but it is now placed inside a beaker, and this beaker contains ethanol, and make sure that the level of ethanol is below the baseline. And after this, we will show the end result. The end result would be the paper is there, we have the baseline, but the sample spot has moved away and it has split into different spots, which are the the colored substances in plants. And we will also mark another line here, which is called the solvent front, the distance traveled by the solvent. So this, the distance from the baseline till the solvent front is called the solvent front, and the distance moved from the baseline till wherever the component of the sample are moved is called the solute front. And we have to calculate the RF value. So here the RF value will be defined as solute front, which is the distance traveled by the solute divided by the solvent front, which is the distance traveled by the solvent. So our diagram is complete. Now we need to put the method down in words. So let's begin. Perform paper chromatography. So we have defined the technique that we will be using here. Okay. Using a pestle and mortar, grind together the plant leaves, sand, and ethanol. Once you have properly ground them, right? then you need to remove any additional ethanol. You throw it away, you decant it, right? Decant additional liquid present. This is not pure ethanol. This will also have extracts of plants in it. So decant additional liquid present. Now what we will do is draw a baseline on the absorbent paper and place a sample spot on it. Let it dry. You have to let it dry before you perform the chromatography. Let it dry. Okay, after you let it dry, now what you will do, place paper in a beaker containing ethanol with level below the baseline. This is important because if the baseline is dipped inside the ethanol, then the sample spot that was dried onto the paper will dissolve in it and the chromatography will not be performed, right? Okay. Now what you'll do, allow ethanol to move up the paper, marking the solvent front just before it reaches the top. So we have mentioned that we mark the solvent front. Now we also have to mention that we need to perform a calculation for the RF value, but we don't have enough space left here. That is why we included the formula of the RF value along with the diagram. So all we need to do here is now mention calculate RF values for each component. And in this way, we have completely written the procedure for performing paper chromatography given the material in this question.